In this video, we're going to prove some laws that make it possible for us to differentiate exponential functions. So first, it's important to know that the derivative of ln x with respect to x is 1 over x. Also, the derivative of e to the x with respect to x is e to the x. And the derivative of b to the x with respect to x is b to the x ln b. And we'll prove all of these rules. And then putting the last rule together with the chain rule, we get this beauty right here. If you're given a function b to the exponent f of x, and there are no x's in b is just a scalar quantity, then the derivative of that will be b to the f of x. In other words, just repeat the function exactly like it is, multiplied by the natural logarithm of the base, and then multiplied by the derivative of the exponent. So let's go through some proofs. In the first proof, we're going to prove that the derivative of ln x with respect to x is 1 over x. To do that, we'll begin by using the definition of derivatives. The derivative of ln x with respect to x, by definition, is the limit as h goes to 0 of f of x plus h minus f of x all over h. So in this case, that means ln of x plus h minus ln of x all over h. Now, recall our rules of logarithms. When you are determining the ln of x plus h and subtracting that by the ln of x, because ln is a logarithm, we can simply say that that's equal to the ln of x plus h over x. So we're going to change our numerator to reflect that. Okay, and that's what we get in this next line. Now, we're then going to change the quantity in the bracket as you see here. X plus h over x is the same as x over x plus h over x. X over x is the same as 1, so we actually get 1 plus h over x. So we're going to change that term inside of the bracket the way you see it here. So in the last step, we had this expression, and now we have this expression. And what we're then going to do is we're going to keep this numerator, which is the ln of 1 plus h over x. And instead of putting it over a denominator of h, the way we have it here, we're simply going to put that 1 over h in front. And so simple rules of fractions, that's clearly an allowable process. We get that expression there. The limit as h goes to 0 of 1 over h times the ln of the quantity 1 plus h over x. Okay, so that's where we've left off. Now, we have a law of logarithms that you probably remember, which says that when you have a logarithm, but you're multiplying it by a quantity, you can simply move that quantity up and put it in the exponent of the argument of your logarithm. So that's what we do in our next step. Okay, we have that expression as you see it right there. Now, we're going to do something kind of interesting. This 1 over h in the exponent, we're going to multiply that by x over x. X over x is equal to 1, certainly. So we're going to multiply by x over x. And we get that expression there. Then, what's kind of interesting is in the next question, instead of calling it 1 over h times x over x, we're going to change the order and call it x over h times 1 over x. So clearly, 1 over h times x over x will give us x over xh, and x over h times 1 over x will give us x over xh as well. So we can definitely change this circled expression here to this circled expression here. And so that's what we do in the next line. Okay. Now, what we're going to do is take this quantity. We said earlier that you can have an exponent and you can move it in front, or if you have a scalar in front, you can move it into the exponent. Well, we're going to take this part of the exponent right here, the 1 over x, and we're going to move it in front the way that we know we're allowed to do from our laws of exponents. And so this is the expression that we have now. The limit as h goes to 0 of 1 over x times the ln of 1 plus h over x quantity to the exponent x over h. Okay, so this is where we've left off. Now, this limit as h goes to 0 right here, that has no impact at all on the quantity 1 over x, because 1 over x is independent of h. So we can actually move that 1 over x in front. And that's what we do in that line. Okay? Now, something that's kind of cool is as h goes to 0, right here, we have h going to 0. We're going to rephrase that as h over x going to 0. And clearly that's true. As a quantity goes to 0, if you put it in the numerator of a fraction, well, that fraction will go to 0 as well. So instead of talking about the limit as h goes to 0, we're going to talk about the limit as h over x goes to 0, because they happen at the same time. So in that next line, all we changed was instead of saying h is going to 0, we said h over x is going to 0. Okay, so here's how we've left it off. Now, what we're going to do is we're going to let w be h over x. If we do that, then notice that this h over x going to 0 is like w going to 0. And this h over x right there is like a w. And this x over h is like a 1 over w, the reciprocal of w. And that's what we get in that next line. Okay, now we're going to move this ln operator. We're going to put it in front of the limit notation, and we're actually allowed to do that. So instead of the limit as w goes to 0 of the natural logarithm of that quantity, we'll say the natural logarithm of the limit as w goes to 0 of that quantity. And we are left with this expression right here. Now, something you might not know is that the limit as w goes to 0 of 1 plus w quantity to the exponent 1 over w actually equals e. And if you recall, e is a scalar, is a irrational number, but it's a constant. It's equal to roughly 2.71828. But it's a non-repeating decimal. You know, in a way, it's like pi, how that is an irrational number, non-repeating decimal. Well, so is e. And the limit as w goes to 0 of 1 plus w quantity to the 1 over w equals that. Now, if you want to see that, if you want to actually see that, you like kind of the visual idea of it, what we're saying is that let this w be a small number and let this w be a small number. So for instance, 0.1, if you evaluate 1 plus 0.1 quantity to the 1 over 0.1, you'll get 2.5937. But now instead of 0.1, make each of those 0.01, you'll get a number that's even closer to e, which is roughly 2.71828. Now let that number be 0.0001, you'll get a number even closer to that. Let w be 0.0001, and you'll get a number even closer to this number. So you see we're always getting closer and closer to e. So at this point, you're probably willing to take my word for it. So what we're really saying at the bottom is that we've got 1 over x times the natural logarithm of this quantity, which is e. Okay, and so there we go. This is what we've got as our expression. And you might remember the natural logarithm of e is simply 1. And the reason for that is perhaps by observation. if we're talking about the ln of e, what we're really saying is the log base e of e. And if you were to let the log base e of e equal a new variable, we'll call it a, then that would mean e to the a was equal to e, so obviously a would equal 1. So obviously the log base e of e equals 1, or in other words, ln e equals 1. So this 1 over x ln e becomes 1 over x times 1, which is 1 over x. And so what we've just shown is that the derivative of ln x with respect to x is equal to 1 over x. Okay, we've accomplished our goal. Now for our second proof, we want to show that the derivative with respect to x of e to the x is e to the x. So what we're going to do is we're going to say let y equal e to the x. And then what we're going to do, something kind of interesting perhaps, we're going to take the natural logarithm of both sides. So instead of y equals e to the x, we'll say the natural logarithm of y is the natural logarithm of e to the x. And that's what we have written here. Now, we know that the natural logarithm of e to the x will equal x. If you need to see proof of that, similar to the one we just showed a little while ago, suppose we said w is the ln of e to the x. That would mean w is the log base e of e to the x. If you recall your logarithms, that would mean e to the w equals e to the x. And if e to the w equals e to the x, then by observation w is x. And since w was the ln of e to the x, therefore the ln of e to the x equals x. So instead of saying the ln of y equals the ln of e to the x, we're going to say the ln of y equals x. And now we're going to be able to do some implicit differentiation. We showed in the last slide that the derivative of ln x with respect to x is 1 over x. Well, technically what that is 1 over x times the derivative of x with respect to x. But we know that the derivative of x with respect to x is 1. So technically what we got there was 1 over x times 1. Well, instead of determining the derivative of ln x with respect to x, if we determine the derivative of ln y with respect to x, we would still say 1 over y, 1 over the block, but now we have to determine the derivative of that block with respect to x. So right here where I have ln y, if I determine the derivative of that with respect to x, I'm going to get 1 over y times dy dx, which is what we've shown here, 1 over y prime. Now, since I determine the derivative of the left side with respect to x, I have to determine the derivative of the right side with respect to x. Well, the derivative of x with respect to x is simply 1. So we get 1 over y times y prime equaling 1. Well, from there, it's a pretty simple process. We're going to multiply both sides by y. So what we do is multiplying the left by y gets us y prime, multiplying the right by y gets us y. And so that's like saying this y prime right here is the derivative with respect to x of e to the x, and this y here is e to the x. So we can say the derivative of e to the x with respect to x is in fact e to the x. Which gets us to our third proof of this video, which is that the derivative with respect to x of b to the x will be b to the x times the natural logarithm of b. So we're going to follow a pretty similar process as we did in the last one. First thing we're going to do, we're going to let y equal b to the x. Now, we have a rule of logarithms that you may need to be reminded of, but there's a rule that says a to the exponent, log base a of b, will always equal b with, appropriate restrictions given that we won't worry about in this space right now. So what we're going to do is, instead of saying b to the x, we're going to say e to the log base e of b to the x, and we're going to say that that equals b to the x. So right here, this b, we're replacing it with b to the x, which means we're replacing that b with b to the x. And instead of a, we're using e in both spaces. So instead of writing b to the x, which we have right here, instead of writing that b to the x, we're going to write e to the log base e of b to the x. But of course, the log base e of something is the ln of something. So we're really going to write it as e to the exponent ln of b to the x. We're going to put that in place of b to the x. And so we're going to say b to the x is e to the exponent ln of b to the x. And so the function that we're going to determine the derivative of is e to the exponent ln of b to the x. So now let's do our work. We're going to, as we know, we're allowed to do with logarithms. If I've got an exponent of ln b to the x, I can instead call that exponent x ln b. And so that's what we're going to show in our next step. Now we're going to use the chain rule. Since the derivative of e to the x with respect to x is e to the x, the chain rule will tell us that the derivative of e to the f of x with respect to x is e to the f of x times the derivative of f of x. In other words, the derivative of e to the f of x with respect to x will be e to the f of x times f prime of x. Now in this case, the exponent is x ln b. In other words, the f of x that I'm referring to is x ln b. And that's kind of like saying ln of b times x. Well, what's the derivative of that? It's simply ln of b. The derivative of a linear function is just the coefficient of x. So since, like it says in this line down here, since the ln of b is just a scalar, the derivative of x ln b with respect to x will just be ln of b. And putting all that together, we get the derivative will be e to the x ln b times the derivative of the exponent, which is ln b. And so we have shown that the derivative is equal to this quantity right there. Now, we're going to now take that x, we're going to move it back up as we know we're allowed to do from our laws of exponents. And we get y prime equals e to the ln of e to the exponent ln of b to the x times ln b. But recall our whole lengthy discussion from earlier, e to the ln of e to the exponent ln of b to the x is just b to the x. We went through that discussion a number of slides ago. So instead of that circled quantity e to the exponent ln of b to the x, we can just replace that with b to the x, and we have now established that the derivative of b to the x, well, where it is, the derivative of b to the x with respect to x is b to the x ln b.